Okay, next we will expand the equation of total flux for the convective diffusion. Okay, so we already derived up until here, so we will further expand the equation. So from the total flux of NA, so total flux of A is equal to diffusion flux of A, which is JA, plus with the convective flux of A, which is CA times the Vm. So Vm, the velocity of the bulk relative to the stationary point. Okay, so for the equation, so we will replace Vm with another equation. So let N be the total convective flux. So N is the total convective flux. So N will be equal to total concentration. We multiply with the velocity of the bulk. Okay, so the velocity of the bulk fluid. Okay, so and it also equal to, when we talk about total convective flux, is also equal to total flux of A, species A, and total flux of species B or component B. Okay, so we rearrange the equation. So we have Vm is equal to Na plus Nb over C. Okay, so this equation will be inserted into this equation. Okay, so it will become Na equal to Ja plus Ca. Vm will be replaced by this equation, Na plus Nb over C. Okay, so it will become this equation. So this Ja, the diffusion flux, will be replaced with the Fick's law. Okay, will be replaced by the Fick's law, and the final equation for diffusion plus convection is this one. So Na is equal to the flux of Ja, negative C dEV. Sorry, this is dAV. So negative C dAV dXA over dZ plus with concentration of A over total concentration times with the Na which is the flux of component A plus with flux of component B. Okay, so this is the final equation. So if I can derive again, so maybe I will go through from the beginning. So for Ja, this is for convection flux. So Ja is equal to dAV times with the concentration of A. Okay, so concentration velocity, if we can draw the total velocity of component A, dA, is equal to the velocity of A due to diffusion plus with the velocity of bulk velocity. Sorry, diffusion of bulk velocity, which is Vm. Okay, so dA is equal to dAV plus Vm. Okay, so we multiply all this term with concentration of A. So Ca Va equal to Ca VAV plus Ca Vm. Okay, so for Ca Va is the total flux. Okay, total flux. This will be the total flux of A, and this will be the Ga, and this is will be Ca Vm. Okay, so Vm, let N will be the total convective flux. So N is equal to total concentration times with the Vm is also equal to Na plus Nb. So if we want Vm, so Na plus Nb is divided by total concentration. So we replace into here. So it will be NA is equal to JA plus CA over C. VM is the NA plus NB. Okay, so the JA we will replace with fixed law. So you know that fixed law is equal to negative C, DAB dXA over dZ. Okay, so you replace this into here, negative C DAB dXA over dZ plus CA over C and A plus NB. So this is the final equation for diffusion plus convection. Okay. So we can summarize that there is difference between JA and NA. So at the beginning we define diffusion using this term, which is the molar flux. Okay, this is JA or molar flux. So what is NA later, and we learn on total flux. So on the convective diffusion, so I introduce you to the NA term. So this is the total flux. Okay, so what is the difference between JA and NA? So JA is the flux of A that occurred due to the concentration gradient, which means that the component of A diffused by itself, okay, due to the concentration gradient. However, for NA is the flux of A relative to stationary fluid. Consider a whole system where there is a moving fluid, which means if we have component A here, component A in water, so both water and A are moving. So for this case, we should use the flux of A and E. Okay. Okay, next we will see the next type of diffusion. So far for gas we already cover on equimolar counter diffusion. So do you remember on DAB also is equal to negative dVA. So for molar flux, JAZ is also equal to negative JVZ. Okay, so this is for equimolar counter diffusion. So next we touch on diffusion plus convection. So this is I introduce you to another term of NA, the flux of A. So where the diffusion of component A happen when the whole fluid is moving. So the component A moving, the fluid is also moving. Okay, so this is the diffusion plus the convection. Next we will see how the diffusion through stagnant fluid in gas. Okay, so diffusion through stagnant non-diffusing B, we call it as gas diffusion. So you can see here for this example, so diffusion of A through stagnant or non-diffusing B at a steady state. So you can see here, for example, if we have a liquid benzene, we call it as a component A, liquid benzene. So liquid benzene will evaporate into the air. So the liquid benzene from point A at the surface of the liquid will evaporate towards point 2. Okay, from point 1 to point 2. So the distance of the evaporation or the diffusion is, we call it at Z2 minus Z1. So this is the distance. Okay, the distance of the diffusion. So the air inside the tube is stagnant. Okay, so we have air here, air filling the container. So when the liquid benzene evaporate, it will pass through the air. So air is not react with the benzene. So air, we call it as stagnant. Okay, so the benzene is evaporating through this stagnant air. So the air is stagnant. So the diffusion path is from point 1 to point 2 across the distance Z2 minus Z1. So this is what we call diffusion through stagnant non-diffusing B. So the non-diffusing B here is referring to the air. Okay, so the diffusion is the benzene. Okay, so for case 2, another example on diffusion through stagnant non-diffusing B. So we have ammonia. So ammonia diffuse through the gas mixture from point 1 into the bulk phase of point 2 at the gas liquid interface, and eventually it will be absorbed into the water. Okay, so for example, if we have ammonia here, ammonia will be mixed with air. Okay, here we have liquid here. So at the upper side of the liquid, we have ammonia and air. So ammonia will be absorbed into the water and it will pass through the air. Okay, so air is assumed to be non-soluble in water. Only ammonia is being soluble in water. So air is not diffused. Air doesn't diffuse. So the non-diffusing component here is air. Okay, air is non-diffusing or the stagnant component here. So the ammonia will diffuse into the water across the path or across the distance. We call it Z2 minus Z1. So this is the distance. Okay. Okay, for the diffusion through stagnant non-diffusing B, so we will begin the equation with the previous equation. I think you still remember this. Okay, so the flux of E is equal to GA plus CA over C NA plus NB. Okay, so this is from the previous equation, convective equation, this one. Okay, so from this one. Okay, next we will bring the equation for the next derivation. Okay, so from this equation we replace GA with the fixed law, so we will have this equation. Okay, so when we have diffusion through stagnant or non-diffusing B, for example, here, okay, the ammonia dissolved into the water and it passed through the air, so air is not diffused. Means only A, component A, which is ammonia, is moving or diffusing. Okay, so here we can say that the flux of B is 0 because the component B, which is the air, I'm referring to the previous example, so B is not moving, means the flux of B is 0. So it will become NA is equal to negative C dAB dXA over dZ plus CA over C and A plus 0. Okay, so the NB is 0. So this equation we substitute the XA with these three equations. Okay, so the CA over C will replace with the PA over P. Here, PA over P, and will become this equation. Okay, this one, PA over P and A, and dXA will replace with XAP over dZ, and C will replace with P over RP. So the final equation will be NA equal to negative DAB over R. Okay, the partial pressure of A over dz. Okay, plus decrease. So this will be the next equation. Okay, so when we rearrange, we don't want the derivative. Okay, so we have to integrate and we must solve the derivative. So when we rearrange and we integrate this equation, and it will become this equation. Okay, I'm not going to show you the detail in the rearrange and integrating. I think quite complicated. So when we rearrange and we integrate, you should know that it will become this equation. This will be the final equation for diffusion of A through non-diffusing B. Okay, so the equation will be dAB P over RT Z2 minus Z1, because we already integrate Z and we already integrate P, so it will become ln P. The capital letter P is total pressure minus the partial pressure of A at point 2, P minus PA1. Okay, so this final equation we can also write in another form. Okay, so we replace the partial pressure with the PBM. So PBM is actually log mean value for the pressure. Okay, so we replace with PBM. So PBM, so we have another equation for PBM equal to PB2 minus PB1 over ln PB2 over PB1. If you have the information for point B, you can use this one. Okay, if you have the equation for point A, you can use this one to calculate PB. So when you have PB, you insert into this equation. You have partial pressure of A1 and partial pressure of A2. You can use this equation. If not, you can always use this equation. It depends on your information available in the equation. Okay, so P partial pressure, the total pressure is equal to the PA plus PA1 plus PB1, and also equal to PA2 plus PB2. Okay, so this will be the final equation. Okay, this is the how we rearrange and we integrate the equation. Okay, maybe I can repeat all over again. So this equation for diffusion through non-diffusing B. So this is the total flux of A is equal to JA plus CA over C and A plus NB. So for non-diffusing B and B, flux will be 0 because it doesn't move, so it will become 0. So this equation will become this. Okay, JA will replace with the fixed law here. Okay, when we replace these three equations into the equation, these three terms into the equation, so we will get this one. Okay, so from this equation we rearrange and we integrate. Okay, so we bring, I think we bring this term to the right. Okay, and we rearrange and we integrate to the respective point PA2 and PA1, and location for Z is from point 1 to point 2. Okay, so this will be the final equation. So this is the how we rearrange and integrate the equation. So this will be the final equation. Okay, so as a conclusion for the gas, so we have two types of diffusion for gas. We have equimolar counter diffusion and we have diffusion through stagnant non-diffusing B. So for the equimolar counter diffusion, I think you can memorize that J is, for example, if GAZ, okay, so it's equal to negative J BZ. Okay, so this is the equimolar contribution. You just put negative for the molar flux. Okay, so this is, I think this is the original equation that we learned from the beginning. Okay, so we integrate. So this is the equimolar contribution for the gas. Okay. we replace the gas constant here. Okay, and for the diffusion through stagnant non-decreasing B, so this will be the final equation. We have two types of equation. So this equation will be in terms of the total pressure, okay, and this will be on ppm, the log mean pressure, log mean value for the pressure. Okay, so this example I will cover during the tutorial.